Sorry. Okay, you can't hear me. Hello, hello. Hello. Sorry to, okay, this is what, so I visited the rooms. I hope maybe you got something done. It's not totally clear to me. I understand it's tricky, but I talked to a couple, there were no questions in the room. I know we only have 15 minutes. It occurred to me, a couple of people were giving me their honest feedback that like, they find it easier when whatever. I'm gonna, thank you for, hello, hello. Okay, we have 13 minutes. I think this kind of time is really worth trying to have sometimes, but obviously it is what we make of it. And I can't, and if the spirit is not moving you in the moment, anyway, whatever. I hope maybe you got something done. I'm not entirely sure that anything got done, but it did occur to me with 14 minutes. I think one thing I can do that's useful for all of you right now, I mean, and let me know, you can hear me and see me, right? I mean, you're there. Like, obviously you're there because you're there, but yes. Okay. Thank you. Thank you. Okay. Thank you. I appreciate it. Okay. And I know today's been sort of whatever, but with 13 minutes, it does occur to me there's one little concrete sort of solution I can give, or one little thing I can explain that might be helpful to some people. It was in, so I'm going to explain something now since there were no questions, something that was involved in homework 2 in the math methods homework, but we never actually got a chance to go over explicitly in class. And wait, and there's a but there is a question. If there, I would rather take your questions than mine. So let me see. Oh yes, I'm sorry. Wait. Okay, good point. Sorry, there's a question in the direct chat. Okay, this is good. If nothing else, this will make our time. There's a question in the direct chat. It's direct chat. I'm not going to say the person's name, but I'm going to read the question because it's totally fair. It is totally fair. Professor, I have a question for part 2, question B1. Like part 2, question B1. It says, does the cosine expression, but there's no cosine expression shown. That's right. That's a total error. Thank you for catching that. You're totally right. In part, so anybody who's listening right now, good catch. In part 2, question B1, and I'll try to correct it in an update. It should just say, does the above expression satisfy the differential equation for harmonic oscillation? Okay, so 2B1 should not say, does the cosine expression? It should just say, does the expression? And it's actually hilarious that of all the questions for anybody to ask me, I'm so pleased that that is the question that you just asked, because this is the part of the exam I was about to sort of give some tips about right now. Like, that's literally the part, because I know we didn't. So I'm going to, yeah, that literal part. Okay, let me literally, my 11-year-old son just discovered recently how to say literally. I'm going to literally spend the 11 minutes that we have to literally go over that literal question that someone in the direct chat who should submit for participation points just asked. Because I think it's a very reason. So okay, we're going to do this right now. I'm going to shut up. Oh, God, what is wrong with me? Don't answer. So we're talking about 2B1. Right. So we are trying to show whether this thing is or is not a harmonic oscillator. Okay, this is not a trick question, and it's not an obvious question. It's not, and it's not like it is a reasonable question, but it's maybe not easy. What we're because yes, the whole thing. So I'm talking again to everybody for 10 minutes. I'm talking about part 2, lowercase b1. I might switch. No, I can't switch screens. Well, here's the thing. Okay, so this is the question. Now, the reason, now your first instinct might be, especially given what the direct chat person was just asking, your first instinct might be, wait, that's like not even a cosine. Every simple harmonic oscillator we've ever done has been a cosine. So like, Obviously, no, you might think, but that's not good enough. That's not the answer. Like what we're really asking here, is the WIQ is the point of this question really is that an expression for x, which when we differentiate it twice with respect to time, do we get back itself times some constant times -1? Like really, truly, like that's what the question really means. What we all really want to know is a simple harmonic oscillator is something that satisfies that differential equation that I just wrote on the board. And in general, again, remember, in general, it doesn't even have to be x, like our dependent variable. For any dependent variable, for any measurable quantity that you might be tracking in the lab as time passes, if that dependent variable can be written as d2 variable over dt squared equals negative constant times the variable, then that variable is oscillating harmonically in time. Like that is like our big lesson here in a way. So we're really at, what we've spent all of our time like finding out in the course is that the cosine expression is a solution to the harmonic oscillator, that it is an expression that works, that satisfies a differential equation, that it is a very good way of describing oscillators. But please remember, and this is like where all the material gets deep and stuff. First, we found that a solution to the oscillator was like x equals x naught cosine omega t. But then we scrambled around and we found that like we could add a constant to the parentheses. We could say x equals x naught cosine omega t plus phi, and it still worked, i.e. we found out that this cosine expression that we're using is a solution, but it's not necessarily the solution or the most general or the only solution. Like that was one important thing of finding out about the phase constant, is that it shows us that just because we have a solution doesn't mean we have all the solutions. In fact, those of you who are really paying attention, and some of you said this early on, once you introduce the phase constant, it really drives home the fact that cosine has always just been a choice of convenience for us, that we actually could have been using sine. Sine also satisfies the differential equation. It's just not as convenient because it starts at 0, blah, blah, blah. But, you know, if you add a pi over 2 as a phase constant to cosine, you end up getting sine anyway. In other words, I'm just trying to say with 6 minutes left, that we've never, ever wanted to believe that we had the only solution in our pocket. We wanted to believe that we understood what it means to be a solution. So the real question is, could an exponential function satisfy? Now, the two things, especially, you know, if I run out of time, the two key facts that I'm going to use to test this function, the two key, or to test any of the functions on this page, these exponential functions, the two key facts are the ones that I wrote right here at the front. Like, first of all, for any, and I'm also going to use the chain rule. You know, we know from calculus that e to the x, if you have y equals e to the x, then dy dx equals e to the x. E to the x is the function that when you differentiate it, you literally get back itself. It's a very good candidate for a function when we're, I mean, it's a very, very good, smart, reasonable choice when we're looking for functions that when you differentiate them a couple of times, you basically get them back themselves. I mean, there's nothing more pure and raw than E when it comes to that. But then, you know, some of the choices on that page and some of the choices in the math homework also throw in an I, which can seem really weird. Like, where's I coming from? The only thing you need to know about I, the number I, the two things you need to know are that it's just a number. It's a constant. I'm not expecting you to know like everything in the universe about imaginary numbers or complex functions or anything like that. But as long as you know that I is a number, it is a constant, and the constant that it is the square root of -1, then that's all you need to take seriously if someone throws it in a function for you. And what you're going to find out right now is, I'm going to cut to the chase. I'm going to do this, but I'm going to say, all right, I'm going to say the answer just in case I run out of time. Hold on, I keep flipping my screens around. I'm going to try to do this quickly in the 4 minutes that I have, but I'll tell you right now, the answer to this one. I'm going to do it again, but just in case we run out of time, for this one that someone in direct chat asked about, this one, the answer is going to be no. Okay, I'm going to tell you the answer is going to be no. It's going to be close, but it's going to be no, because we're going to differentiate this thing. The way we're going to find out is we're going to differentiate. We're going to see what happens when you take derivatives with respect to time. And just in case I run out of time again, I'm going to tell you when I take two derivatives. Well, here we go. Well, I'm going to tell you that when I take two derivatives of this function, I'm going to get back something that does look remarkably, that does look like itself times a constant. But I don't think there's going to be the proper negative sign in my final answer. So it'll almost look like d2x dt squared equals, it will look like d2x dt squared equals omega squared times itself times x, but there won't be the negative sign there. So the answer is going to be no. And like, that is a good enough reason to say no. Like in other words, it won't be Hooke's law. It won't be a harmonic oscillator. It won't be always restoring in. The negative sign will be missing. But I will tell you in advance, again, since we have 2 minutes more, that the answer to the one above, the one that has the I in it, that one will work. It turns out that because when you multiply the square root of -1 by the square root of -1, when you square it, you get -1. So that will force a negative sign that will solve our problems. In other words, it turns out, I guess I'm summarizing here, but it turns out that exponentials, when they're written with imaginaries, when you combine exponentials and imaginaries in a clever way, you get the equivalent of trigonometrics. It turns out that e to the x almost acts like a cosine, but it doesn't achieve the negative sign properties that it needs to, but e to the ix does. So the answer to 2b1 is going to be no. So, and there won't be a period therefore, so there's no answer to 2. But the answer to 2a2 will be yes. All right, I have like 1 minute. I don't know if I can do this quickly now, but what you do is you take derivatives. So I'll just, and if anybody has to leave now, you can leave, but I'm just going to take the derivative here just to show you, but thank you but that's a great question. The person who put that question really should submit for points, please. But here we go. So right, I'm taking one okay, I'm just looking to see if anybody's still here. Okay, so I take one derivative, right? I'm doing derivative of e to the blah is e to the blah, but there's chain rule. So I have to take out, I have to multiply everything by whatever is the derivative of what's inside. The derivative of what's inside is kq over r cubed, because all of that is a constant, but the pi squared over 9 is like a phase constant. It's a constant, it doesn't come out. So then I do this again. Okay. Oh yeah, okay, cool. And then I'm gonna go. Sorry, but yes, but anybody who has to go. I know I'm now dragging this out, but the answer will be no, it won't work. But the answer with there's an I in there, it will work. So I do this again. Okay, so I'm just going to summarize. And again, I'll hang out for a second if anybody of you has questions. But the answer to that one is no, it does not satisfy. Literally because that plus sign there before the K. If that plus sign before the KQ squared over R3 were a negative sign, then I would say, yes, it is a simple harmonic oscillator. And again, honestly, that's what will have happened in the part above on the sheet when there was an I in there. The I will actually take care of that for us, whether you, and that's actually super cool if this were a math class, but whether you think it's cool or not, it's the case. So thank you for your patience and everything. And I'm going to thank you, and have a great week. Sorry, I'm so spazzy. I'm going to hang out for a second for anybody who has extra. Thank you. Awesome. Thank you. And this little thing I'll try to post too. I think I recorded. Okay, cool. Thank you guys. Okay.
All right. So Professor.
Yes, question. Yes.
So for questions like this, can we, instead of showing the math, like if we know, like what basically what you just said about the exponential functions, like what if we just know that it doesn't have the negative capabilities unless there's an I present or it's working with imaginary numbers? Can we just explain that out, or do we have to show the math?
I mean, that's a very fair question. And here's my really I mean, that is a fair question. And especially because I do believe that you do. Like, but here's why this is a tricky question. What my most honest answer is, if you really explained it so articulately and like precisely that you did it in English, you wouldn't, and you even literally in English said like at what step that happens and that it's because of chain rule or this or that, then I would say that's fine. It doesn't literally have to be math. It could be English, but that's really risky. I would really rather you show the math, and here's why. Like, again, in your particular case, I actually do believe that you do get it. So it's not that you have to show me the math because I otherwise think like you're cheating or something. I really do think you get it. In fact, to be really honest, I don't even think you could just ask what you just asked unless you got what I was saying. I mean, really. But I would say though, when you're doing the exam, and since you do have time, if that decision, I mean, if that question even enters your mind, I would do two things. And again, not to take up too much of your time, but I think it really is a fair question, especially for people who do know what's going on. Ask yourself two things. Like, one, say you were trying to show this to somebody else in the class, like you were actually trying to help somebody, right? Like before the exam or whatever, during the exam. Like, the thing is, you know in your heart that you could say anything like what you just said to me, and you'd be telling the truth, and you'd be knowing what you were talking about. But until you actually wrote the math thing down, they would either not believe you or they would believe you, but they'd feel dismayed because they'd feel like there's no way they would get what you were talking about until they saw the one line of the math, and then they would have your trust, or I mean, you would have their trust. Just like with you, honestly, what I really think is, and I really mean this, I really think you do get it. And I don't think you need to see that math step anymore probably in your life for you to believe me. Like, it's like boring to you at this point. But I think even you only get it because at one point in your life, you saw the math step. And like, same thing with me. Like, and this is like the real, and I'm really being, I don't know why I'm being so honest, but like, this is like the really tricky, weird thing, because like, for many years, like when I like allocate time badly, like today and stuff, what I know in my heart, I mean, I know how boring it is to keep seeing that math step over and people need to go and all that kind of thing. And I know that like a lot of people in the room, like you are like, oh my God, yeah, no, we get it. But like, I also know in my heart at this point that there are people in the room that totally literally like, it's like completely meaningless to them until they see that one step. And then it's perfect. Then it all falls into place. And then at least, you know, for that question, like then they have the same mindset as you. So what I'm really saying is that at some level, at some level, the reason you don't want to give me that detail, maybe, it's not even because you're lazy, and it's not even because it's going to take too much of your time, because like it won't, like, but at some level, you're thinking in your heart that now that you really get it, you want to think of it in the smart way. And you're thinking of it as kind of like the dumb, obvious way just to show the math. And I'm going out on a limb here, but I'm thinking that you're kind of maybe doing the same thing that I sometimes do as a teacher by accident, which is thinking like, if you really want to be sophisticated, you'll show that you know it even without that drudgery. But I'm kind of here to say, like, actually, all the sophistication pivots on the drudgery. Like, you won't actually be any stupider for doing it, or you won't be any less impressive or less original if you want to say more around it. Like, then like, or show why it's always got to be true, or say go for it. But like, so that's a long, long way of saying, like, I think when in doubt, if that question occurs to you, just do the thing, really, but then do more, sure, if you want. But am I making any, but that's my answer. Okay, all right, sorry. I know it took so long, but I know that I'm saying this to both of you guys. Like, the whole art of getting smarter is allowing yourself to get stupider. Like, really. Oh, there's a game turn. Okay, I've got to do a game turn. Yes, thank you for reminding. And thank you for both of you, thank you for the great questions today. Seriously, and sorry to take so long with that. All right, I'm gonna do a game turn. I'm gonna go because I'm awkwardizing myself. Okay, both of you have a great day. I'll do the game turn thing right now. Thank you for reminding. Or wait, wait, did you have a different question? I'm sorry. Okay. Sorry. No, but if you have a different question, you can ask a different question. Your question was great today, but it was perfect. Wichi, if you're still there, I don't know. No, okay. That was great though, seriously. Okay. And thank you for agreeing with my statement. Okay, I'm totally gonna go. Oh.